This paper was published in Monthly Notices of the Royal Astronomical Society. It explores topics such as accretion disk, magnetically arrested disk, NAD, simulation resolution, turbulent convection, and jet sheath. Let's first hear a simple explanation.
Can strong magnetic fields clog the gas around a black hole and cause eruptions? Imagine water swirling down a drain. A black hole pulls in gas the same way, and that spinning gas makes a flat, glowing whirlpool called an accretion disk. Some disks have very strong, organized magnetic fields. Think of invisible rubber bands wrapped around the gas. When these fields are strong enough, they can act like a clog in the drain and slow down the flow. Scientists call this a magnetically arrested disk, MAD. The clogged gas can build up and then burst out in sudden eruptions, kind of like a shaken soda bottle popping its cap. To study these things, scientists use computer simulations, which are like video games that follow tiny bits of gas. Resolution in a simulation is like the number of pixels in a picture. More pixels, higher resolution shows smaller details. When scientists made their simulations much sharper, about 10 times more pixels, the big picture properties of the disks stayed the same, but new details appeared. The finer view showed small turbulent motions that can push angular momentum inward, like little whirlpools moving the spin of the gas differently than expected. During eruptions, the sides of magnetic tubes mix more, and wave-like ripples appear along the edge of the jets that shoot away from the black hole. At higher resolution, the jet's outer layer, the sheath, looks thinner, hotter, less magnetized, and more jumpy over time. These detailed differences could change how much light and what kind of light we would expect to see. This matters because real telescopes, like the Event Horizon Telescope, are starting to take pictures of the gas near black holes. If sharper simulations show new behavior, then our predictions of what telescopes should see can change. It's like the difference between a blurry photo and a sharp one. Finer details can tell us how black holes grow, how they launch jets, and how they affect nearby space. Better, high-resolution simulations help scientists understand and explain the real signals from the universe.
Ready for the next level? Here comes the science explained with real research terms.
What happens in a black hole's disk when strong magnetic fields stop the flow? A magnetically arrested disk. Imagine water swirling down a drain. Gas and dust spiral into a black hole in a similar way, forming an accretion disk. Around some black holes, the magnetic field is so strong, it acts like a plug or a gate, slowing or stopping the flow. We call this a magnetically arrested disk, MAD. To study these systems, scientists run computer models that combine Einstein's gravity and magnetized plasma physics, called GRMHD simulations. Resolution in these simulations is like the number of pixels in a camera. More pixels let you see finer ripples and small-scale turbulence. If the resolution is too low, important details like mixing, small eruptions, and thin layers can be missed. When the team increased the simulation detail by about 10 times, the average disk properties stayed about the same, showing the big picture is stable. But the higher resolution runs revealed new small-scale behaviors. Turbulent convection that can carry angular momentum inward, mixing where magnetic flux tubes erupt, and clear wave-like ripples in the jet's outer layer, the sheath. At higher detail, the jet sheath got thinner, hotter, less dominated by magnetic field, and more variable. These small changes can alter how and where energy is turned into heat and light around the black hole. This matters because telescopes like the Event Horizon Telescope are now seeing polarization and fine structure near black holes, M87* and SGRA*. If low-resolution models miss important ripples or mixing, predictions of the light and polarization we should see can be wrong. Think of comparing a blurry photo to a sharp one. The sharp photo can reveal small but important features. Better resolved simulations help us understand how black holes launch jets, heat plasma, and produce the signals we observe, improving how we read the universe's photos of black holes.
That's it for today's paper. Thanks for tuning in. See you next time.